Welcome back to Lecture 1, Organic Contaminants. In Section 5, we'll talk about partitioning of organic contaminants between the phases that we mentioned in Section 3. We'll also start talking about the partitioning itself with solubility and the dissolution of the NAPL phase. It's very useful to describe the partitioning of organics between these phases, in part because remedial technologies often make use of the transfer of a chemical from one phase to another so it can be removed. Groundwater systems tend to be slow, so the equilibrium between these phases may at least be approached. In any event, the equilibrium is a state that the system tends to go to naturally, so it's useful to consider that state. We're going to consider 4 partitionings: solubility, the partitioning of the chemical between the NAPL and the water; KD, or absorption, the partitioning of the chemical between water and the sorbed phase, or the solid phase; vapor pressure tells us the partitioning between the NAPL and the vapor if it's present; and something called Henry's law constant tells us the partitioning between the aqueous phase and the vapor phase. We'll go through all 4 of those in the following lectures. Again, why do we want to make this effort? Well, in many cases, we're using a mobile phase to flush contaminants out of a system. Water or gas are 2 typical mobile phases. If we're dealing with NAPLs, the NAPL has to partition into the mobile phase, and that's described by these partitioning coefficients we'll discuss. Again, we might directly remove NAPL by partitioning it into the vapor phase or into the water phase. Again, that's going to be covered by these parameters. In the plume, we can apply sparging. We do it rarely, but it's useful to apply in some cases. That, again, tends to transfer the chemical from the aqueous phase to the vapor phase, so we need to know something about that transfer. In the opposite direction, if we wanted to add oxygen to the subsurface to enhance aerobic biodegradation, we would be interested in the transfer between the vapor phase and the aqueous phase. Again, that's still covered by our partitioning coefficients. So lots of reasons why partitioning is useful to examine. Well, there are some useful calculators that are available, and we'll use those to get a quick view of how certain contaminants might partition between phases at equilibrium. Let's look at one case that's handled in this calculator. It's a gasoline that contains methyl tert butyl ether, MTBE. And let's treat it as occurring in a sandy soil that has 30% porosity, has some organic carbon, which we'll see later is important in terms of absorption, and has pore space of 30%, 20% of which has got air, 70% water, 10% contains actual gasoline NAPL. We can use this calculator to try and determine where's the benzene. Benzene's quite soluble for an organic chemical. But where is it? Well, the calculator tells us that virtually all the benzene occurs in the NAPL phase. Even though it has a significant solubility, very little of it is in the water. What about MTBE? Well, MTBE is 20 times as soluble as gasoline. Where does it occur? Well, again, virtually all of it occurs in the NAPL and in the water. Again, the NAPL still dominates. So even chemicals that are very soluble can still be found mainly in the NAPL under these sorts of conditions. So let's look at a remedial technology. So let's take that same gasoline, that same soil, and let's add air by air sparging. So one of the things we do in sparging is increase the proportion of air in the pore space at the loss of water. So what we have now is pore space with 80% air, 10% water, 10% NAPL. Let's see how the calculator tells us the phases are distributed. Where's the benzene now? Well, just like the last case, virtually all of it is still in the NAPL. Very little of it is in the air phase. So this sparging technology is an attempt to transfer the benzene from the NAPL to the air so that we can remove it in the flowing air. Probably going to take a lot of air to remove this benzene from this system. So you can see that simple partitioning gives us a very good clue on how to approach remediation of certain chemicals. So let's talk about solubility, the partitioning of a chemical between the napple and water. It's usefully described by something that's analogous to Royolt's law. That is, the concentration of the chemical in the aqueous phase is equal to something called the mole fraction of that chemical in the napple phase times the pure phase solubility of that chemical. Now, the pure phase solubility of that chemical is well described in the literature. So for virtually every chemical, we can determine the solubility. To determine how much of that chemical is in water, we still need to measure or determine something called the mole fraction. That is the number of moles of the chemical of interest divided by the total number of moles that are present, mole fraction. Here's a definition of solubility. It's usually measured or reported at about 25 degrees centigrade and 1 atmosphere pressure. And that's okay for most warm groundwater situations. These reported solubilities are useful, except in 2 cases. If the chemical can occur as a solid at that temperature, or as a gas at that temperature, then we have to fiddle around a little bit with the reported solubility. That's because when we dissolve these chemicals into water, it's presumed that they're coming from a liquid state and staying in a liquid state. Well, if they exist as a solid or a gas, we're going to have to convert them to their equivalent solubility in a liquid state. In short, what that means is that for something like naphthalene, which is a solid at room temperature and cooler, that it's really an effective liquid solubility we need. So if you look up the solubility of naphthalene, it's commonly reported at about 30 milligrams per liter. When in fact, if it's found in a napple, in a liquid napple, its effective solubility is really 150 milligrams per liter. This is a significant difference, and it leads to improved interpretations. That is, when we see fairly high concentrations of naphthalene in water, it looks unreasonably high if that was its solubility, but in fact its effective solubility is 150 milligrams per liter, and that usually rationalizes most field cases. Here's a series of chemical groups taken from a textbook. It's a useful way of looking at chemicals. Chlorinated solvents, petroleum hydrocarbons, PCBs, PAHs, aliphatic hydrocarbons. And here's a line that I've put together from my experience. I'm considering that chemicals on this side of the line are not soluble enough in groundwater to be a problem, whereas chemicals on this side of the line are soluble enough to be a problem for groundwater. Now that line's very arbitrary. You may move it over a little bit one way or another. But for instance, if we look at PAHs, 2 and 3 ring PAHs are a problem in groundwater. 5 and 6 ring PAHs are not soluble enough in water to really exist at hazardous concentrations. So things like benzoate pyrene really aren't of interest to me in groundwater. They're a soil problem. When we have light petroleum hydrocarbon spills, gasoline, diesel, things like that, our attention often focuses on a group of compounds, the monoaromatic hydrocarbons, the benzene ring substitutions on the ring. Benzene, toluene, ethylbenzene, xylenes, called BTECs. Well, we can get a sense of why that's not unreasonable if we look at a gas chromatogram of gasoline. This is a typical analysis of gasoline, and each of those peaks is 1 or maybe 2 compounds, and the peak height is proportional to the portion of those chemicals in the mixture. And you can see that there's lots of chemicals in the mixture, too many for hydrogeologists. If we take that gasoline and equilibrate it with water, and then analyze the organic chemicals that are in the water, we end up with a very much more simple story. The main peaks are labeled here: benzene, toluene, ethylbenzene, and xylenes. So you can see that the process of dissolving the napple into water creates a much simpler mixture, a mixture that hydrogeologists can likely deal with. So BTX has really become the focus of gasoline contamination monitoring. Again, another view of hydrocarbon solubility. There's benzene that we were talking about. It's got 6 carbons. If we go down to the 6-carbon normal alkane, which is hexane, we find that it's 2 orders of magnitude less soluble than benzene. And you can see that the BTX, or substituted monoaromatics, are much more soluble than their equivalent normal alkanes. That's again why we focus on the more soluble compounds, as well as the fact that they're more toxic than most of the other hydrocarbons. Benzoate pyrene is way down over here, many orders of magnitude less soluble than benzene. So we'll carry on this discussion in the next section. Thank you.